morning. My name is Dachuan Shi from Technical University of Berlin. Today, I'm very happy to present you our empirical study on the robustness of machine learning approaches for fault diagnosis on the railway operational conditions. At first, we will briefly introduce you the common approaches for machine fault diagnosis. Next, we will overview our research method for empirical studies. Afterwards, we will present you the experiments and the results. Finally, we discuss the results and draw the conclusions. Machine fault diagnosis is to use sensor to measure the relevant parameters. For instance, for rotating machine, it is very common to use accelerometers for vibration monitoring. The vibration data will be fed into a model for automatic diagnosis. Actually, the diagnostic problem is a classification problem. One of the class must be the normal condition of the machine. Other classes could be different failure modes of the machine. As a classification in other domain, the deep learning has become the state-of-the-art approach for end-to-end diagnosis. However, when we are going to deploy the deep learning models for railway freight wagons, we got many challenges in practice. Here, we will show you two examples. Normally, we install the sensors on the bogie for vibration monitoring. Bogie is the running gear and the most important part of the wagon. In practice, it is extremely difficult to collect faulty data due to the cost, operational issues, and the safety issues. We can only do the experiments on one or several wagons. Once the models are trained on the training data, we have to deploy the models on many different wagons and bogies, which could have different dynamic characteristics. That means it results in differences between training and the testing data distributions. Furthermore, the wagon is running on the track. The track condition can also be very different. The track can in a good condition. There also could be severe track irregularities or real defects, which can be regarded as signal interferences, causing abnormal vibration excitation on the wagons. In summary, the conditional variations in practice can result in the difference between training and test data distributions. We expect the diagnostic model can be robust to have a similar performance when tested within and outside the training data distribution. That's the reason why we conduct this empirical study. We want to answer the question if the deep learning diagnostic model robust to conditional variations. The idea of an empirical study is to test several state-of-the-art approaches for machine fault diagnosis on conditional variations which can happen in railway normal operations. As a baseline models, we select the residual convolutional neural network as a backbone. The ResNet consists of 3 residual blocks for future extraction. After global average polling, there's a fully connected layer for classification. In the first model, the input data is the raw vibration data. We also consider if the signal processing techniques can affect the robustness of the models. Therefore, we use a short-time Fourier transform to get frequency spectrum as an input for ResNet. We also use a wavelet package transform to get different scalars of a wavelet coefficient as the input for ResNet. In the last model, we consider the conventional machine learning approaches for diagnosis. That means we manually define features from envelope spectrum and use the gradient boosting decision tree as a classifier. All the baseline models have been validated in the era of time series classification or machine fault diagnosis. In the study, we focus on a very common failure of a freight wagon, that is a wheel flat. Wheel flat is a flat spot on the running surface of wheels, causing impulsive peaks. We spent a lot of efforts for data collection. In this study, we mainly use the following 4 datasets. The M1 is measured on a tank wagon with a standard 25 wide 25 bogie. We manually created a synthetic wheel flat with a 20 mm length. In M2 datasets, we also created a synthetic wheel flat with a length of 50 mm on a hoop wagon with a standard bogie. In M3, the measurement was conducted on a newly designed bogie with a natural wheel flat with a length of 60 mm. In M4 dataset, the measurement was done on a very old tank wagon with a UIC bogie. There were 2 adjacent wheel flats with a length of 50 mm. We defined 3 types of conditional variations. The variation of a vehicle speeds affects the amplitude of a wheel flat peaks and the rotational frequency. The variation of a track and rear conditions can be regarded as signal interferences, as previously presented. The variation of a fault and wagon conditions affects the amplitude and the shape of the wheel flat signals. For each conditional variation, we conduct an experiment. In the first experiment, we show 2 examples of wheel flat signals at a low and high speed respectively. No matter it is a raw data in time domain or wheel flat coefficient or frequency spectrum, the wheel flat characteristics are always visible. We train all models on the data at higher speed ranges between 55 and 95 km per hour. When we test the models on the data in the same speed range, all the models achieved satisfied detection accuracy. However, the detection accuracy decreases with the decrease of speeds. That means when the difference between test data distributions and trained data distributions increases, the model performance decreases significantly. In comparison to 3 ResNet-based models, the GBDT with handcrafted features has achieved much better robustness. In the second experiment, we plot 4 examples from 4 datasets respectively. From M1 to M3, there's only 1 wheel flat. The amplitude of wheel flat peaks increases with the increase of wheel flat size. In M2, there are 2 wheel flats. The shape and amplitude of the peaks is different. However, when we fit the data into the model, we have normalized the data according to the mean value and the standard deviations. That means the amplitude shall not play an important role. For human being, we can recognize easily the wheel flat characteristic in all 4 datasets. However, when we train the models on the M1 datasets and test on other datasets, none of models can achieve satisfied performance on all datasets. GBDT with handcrafted features works on M2 and M3, but fails on M4. The 3 ResNet-based models failed on both M2 and M4. In the third experiment, we plot the typical signal interferences caused by variation of track and rear conditions. In the top left diagram, the T1 is the wheel flat signal under interferences, which can be caused by severe track irregularity. In T2, it is a normal data on the inferences caused by track irregularity. T3 is the impulsive inferences, which can be caused by real defects. T4 is the several impulsive inferences, which look similar to well-fed signal. We trained all models on T0 subsets. T0 is a clear subset manually selected from the M1 datasets without any signal inferences. All the models has achieved satisfied accuracy above 99% on T0. Surprisingly, in this case, all three ResNet models has a much better robustness than GBDT with handcrafted features. We were wondering the reason of robustness problem. Therefore, we visualize activation layers within the neural network. In this example, the input welfare signal is from M1 at low speeds. ResNet is trained at high speeds. We visualize the last activation layer before classification layer and randomly select 9 future maps. It seems the neural network has eliminated the noise information and strengthens the well-fed characteristic of periodical peaks. The most features look well, however the classification fails. In next example, we select 2 samples from M3, and the ResNet is trained in M1. When we fit the samples into ResNet, one sample has been correctly identified as a well-fed, and the other one fails. Therefore, we concluded the robustness problem of CNN diagnostic models lies in the classify rather than feature extraction. In the previous experiment results, we have learned the CNN models are less robust than models with handcrafted features under the conditional variations. However, the CNN models are more robust under signal interferences. The pre-processing by using signal processing techniques cannot improve the robustness. That's all. Thank you for your attention. You can find more details on our papers. If you have any questions, you can contact me. Bye bye. Have a nice day.